Hello. Today we'll be discussing the paper on the value of oversampling for deep learning and software defect prediction. This was published at ICSE last year. I'm Rahul Yarida, and I co-authored this with Dr. Tim Menzies. How do you deal with a dataset like defect prediction datasets? We use the Promise repository, which has class imbalance issues. A mainstream way of doing this is using oversampling. You could use something like random oversampling, which goes to each point in the minority class and then adds more points with the same class to the dataset. You can do this in a more efficient way with neural networks in doing something called a weighted loss function in the top left. Suppose we have a loss function L that we're trying to optimize. You can split that into one for the minority class, C0, and one for the non-minority class, which is not C0. For the minority class, suppose n is the fraction of samples belonging to the minority class, you can add in a wi over n term where wi is the weight. It turns out the actual choice of this wi doesn't really matter, so we stuck with the 1. But the 1 over n term does matter. It turns out doing so doesn't really help our case much. So we follow the recommendations of literature. In row number 4, you'll see that we use hyperparameter optimization and SMOTE, which is a more clever oversampling technique. That didn't help us either, although it got us a better IQR. How do we fix this? Well, in the bottom right, you'll see in the first figure that this is the decision boundary when we use oversampling and hyperparameter optimization. It's a pretty bad decision boundary because although it gets all the minority samples 1 correct, the orange samples, it doesn't get many of the blue samples correct. How do we fix this? Well, one way to realize this is if you look at the boundaries of these points, maybe you want the decision boundary to be further away from the data sample, something like an SVM, which is a maximum margin classifier. So we want to push the decision boundary away from these samples as much as possible so that we have a gap or a buffer between the samples and the decision boundary. This way, if a new test sample comes in which is close to a sample and is the same class, it doesn't get misclassified because it's now split by the decision boundary. How do we do this? We can use what we called fuzzy sampling in the paper. For each row or each sample in the minority class, you go concentrically around it in different boxes. For each box, you add a certain number of points which follows a weighted decay. In doing so, you push the decision boundary away, and you also have an oversampling effect. It turns out this reverses the class imbalance. Because of that, we now have to use some form of oversampling again so that we fix the class imbalance issue caused by fuzzy sampling. When we did this along with hyperparameter optimization, we achieved strong results. But we can do better still. We can do the same for the majority class. If we push the decision boundary away from the minority class and that improved the results, it's only natural to assume that pushing the decision boundary away from the majority class would also improve performance. Therefore, in the last row, which is what we're calling ghost, you'll see that we applied fuzzy sampling twice, once for the majority class and once for the minority class. We then applied SMOTE, which fixes the class imbalance issue. We used a feed-forward network, which was tuned using hyperparameter optimization. Specifically, we used the Dodge hyperparameter optimizer published in TSC. And we also used the weighted loss function. This yielded a median F1 score of 80% and an IQR of 25%. This achieved the state-of-the-art result, beating a prior work that used a deep belief network, which was also much slower than our proposed approach. This figure on the bottom right will show you the final decision boundary, which is a much cleaner approach than the one on the left. You can find the full paper at this first link. You can find a demo of fuzzy sampling in the second link, and you can email us at any of these 2 email IDs. Have a good day.